All right, so this week we're going to finish up chapter 4. So we'll look at sections 4.3 and 4.4. First day we'll do 4.3, and then we'll spend the next 2 days on 4.4. So in 4.3, we're going to be looking at solving equations. Those we'll do algebraically. Inequalities, we're going to solve graphically. So we're going to have equations that have lots of fractions in them, okay, like equations like that. But the goal is going to be to try to get rid of all the fractions, and that's going to make the problem easier to solve. Okay, so I'm going to show you when you have an equation with variables, like especially in the denominator, how we can get rid of them, and we won't have any fractions left. All right, so the first problem we're going to take a look at is a word problem. It involves distance, rate, and time. So if you don't know the distance, rate, and time formula, you probably want to copy that down. It's D equals RT. D is distance, R is the rate or the speed, and T is time. Bless you. All right, so what's going to happen in our problem is that Sue is going to be taking a trip. And to do her trip, she's going to take 2 modes of transportation. She's going to drive in a car for part of the trip, and then she's going to get on a train to do the rest of the trip. Okay, so she's going to take a car and a train, and I'm going to give you a little bit of information about each mode of transportation. So it says that Sue drove 30 miles, okay, that's in her car to the train station, and then got on the train. In all, she traveled 120 miles. Okay, that was the total length of the trip, including the amount she drove and the amount she traveled by train. We don't know the speed of either vehicle, but what we do know is the average rate of the train is 20 miles per hour faster than the car. Okay, that's all we know. Okay, so that's the word problem. They want us to come up with a formula that's going to represent the total time it takes for her to make this trip. So it has to take into account the fact that she's traveling by car and train. It's going to take, and the distance of 120 miles, and the fact she did 30 of it by car. Okay, so we got to take all that into account. So the first thing that we're going to need is a variable. Our variable, we're going to use x as the letter. And x could actually represent 2 different things here. What are the 2 things that we don't know in this problem? We don't know
rate and time.
Okay, so we don't know the rate or the time. Let's focus on just the rate. Can somebody tell me what's a rate that we don't know in this problem? Yeah?
The average rate of the car.
Perfect. Yeah, we don't know the rate of the car, so that's one speed we don't know. We also don't know
Speed of the train.
we don't know the speed of the train. So we don't know either rate. So we're going to let our variable be one of them. Okay. In this problem, I think they said let x be the speed of the car. So when we set this problem up, we're going to be trying to solve for the speed of the car. If you want the speed of the train when you're done, well, then all you have to do is add 20. So x will be the speed of the car. All right, so first thing we'll do is let's make a table and see if we can describe what we're going to need to figure out time. That's what we have to figure out. We need a formula for time. The formula I gave you up above is for distance. It's distance equals rate times time. If I wanted to get t by itself, okay, which that's what we need to do. We need a formula for time, not for distance. How would you get the t by itself here. Yep.
You would divide the distance by rate.
Right. Divide both sides by r. And that's how we're going to need to use the formula I gave you. So we're going to have to find the distance for the train in the car, and then the speed of the train in the car. And if you divide distance by speed, you get the time. Okay, so let's start with the car. Okay, so the car is going to have distance that it travels and a speed. Okay, distance in our formula, that's going to be the d. And speed is going to be the r. So I'm just trying to make a table to organize what I kind of know about the car and about the train. Let's start with the distance for the car. What do we know about the distance that Sue traveled by car?
30 minutes.
Yep, we know it's 30 miles. We've got a number for that. And now let's look at the speed of the car. What do they tell us about the speed of the car?
20 miles slower than the train.
Okay, it's 20 faster than the train. And do they tell us anything else?
It's 20 slower than the train.
Oh, it's 20, yeah, 20 slower, yeah. Train is 20 faster. And do they give us a way to represent the speed of the car? X. They tell you to let X be the speed of the car. Okay. Now let's look at the train. Do we know the distance that she traveled by train?
Yeah.
How much is that?
90.
Right, it's going to be 90 because she did 120 total. 30 of it was by car, so the rest of it must have been by train. So she did 90 miles by train. And how would we write the speed of the train if it's 20 faster than the car?
X plus 20.
X plus 20. Okay, so now we've got all our information kind of organized into a chart. We know, or we at least have a way to represent the distance and the speed for the car and the distance and the speed for the train. If you can write down distance and speed, then you can figure out time. Okay. So that's what we'll do now. All right, so let's do the total time for the trip. We're going to have to add two things together. First, we have to figure out how much time that she spends what? Traveling, a little more specific.
In the car.
In the car. So we need the time she's in the car, plus we need the time on the train. And the variable that we're going to use is x. Okay, let's figure out the time she spends in the car. Time is distance divided by rate. What's the distance she traveled in the car?
30 miles.
30. And what's the speed of the car? So divide the two, and that's your time. Distance divided by rate, that's the time she spends in the car. We don't know the speed of the car yet, but that's fine. That's that. When we do know it, we can plug it in, and that's the time. Okay, let's do the same thing for the train. So again, the time she spends in the train is distance divided by speed. What's the distance the train goes? 90. And what's the speed of the train? X plus 20. And there is a formula that will calculate the total time of the trip. We just need to fill in the speed of the car, and then we can figure it out. Any questions how we got the time of the car, the time of the train, or why we had to add the two times together to get the total time for the trip? Okay, so in example one, that's all they want us to do is find, we actually found an equation, not an expression. But we have an equation, and that's it. So we're done example one. So now I want to take a look at that, and I want to see if we can figure out some of the things that we did with that last week. Okay. We're not going to graph it by hand, but we are going to find the end behavior model, the zeros, and the asymptotes. All right. Now, for some of this, It would be easier if we had these two things together as one fraction. But in order to put two fractions together, you got to make sure you have a what? If you want to add two fractions up.
Common denominator.
Yeah, you need to have a common denominator. So if you've got two fractions like that and you want to add them up, the easiest way to find a common denominator is to multiply the two denominators you have together. And in that case, it would be 15. So then this fraction, you'd have to multiply 3 times 5 and 2 times 5. And then this fraction, you'd multiply by 3. So what happens is each fraction gets multiplied by the other denominator. So the left fraction got multiplied by the 5s, and the right fraction got multiplied by the 3s. We're going to do exactly the same thing there to get the common denominator. Okay, so our common denominator is going to be the product of the two that we have. What are my two denominators right now? X times x plus 20. So let's multiply them together. Okay, just like doing 3 times 5. There's your common one. And now each one of these fractions is going to get multiplied in the top and the bottom by the other denominator. So what would I multiply the top and the bottom by in the left fraction? Yep, so we're going to multiply by x plus 20. So that's like the 5 and the 5 came from the other denominator. And what would we multiply top and bottom by on the right fraction? X. That's like multiplying by the 3 and the 3 from the other fraction. Okay, so we already have the bottom. That's x times x plus 20. We can distribute that later if we want. Let's do this part out. 30 times x gives me how much?
30x.
I'm just going to put that over here for a second. 30x. And what's 30 times 20? 600. So that's this part. And then I have that part, 90 times x. Yeah. And when you combine like terms, the only two you can combine are 30x and 90x, which is how much?
20x.
Yep. Okay. So that's exactly the same equation that we just came up with. All we did was put the two fractions together as one. And why did we do that? Well, it makes finding some of these things a little easier. Not all of them, but some of them. Let's do the EBM first. So remember, EBM stands for End Behavior Model, and it's the highest degree term in the top divided by the highest degree term in the bottom. What's the highest degree term in the top?
X.
What is it?
X.
So we need the whole term,
120x.
120x. Okay. That has an exponent of 1. So this term is degree 1. What about the 600? It doesn't have an x. So what's the degree on that?
0.
That's degree 0. So the term with the highest degree is 120x. So 120x over. And what's the highest degree term in the bottom? And we got to be careful because it's not done out. So you got to think if you did that out,
X squared.
it would be x squared. Yep. And then the top and the bottom both have what in common?
Yes.
They both have 1x in common. So you can cancel that x and that x. And your EBM is 120 over x. Okay, we did that last week. Okay, once you find your EBM, you can use that to then find your horizontal asymptote. Okay, horizontal asymptote is an equation, and when we write it down, does anybody remember for a horizontal line, is it x equals or is it y equals?
Y.
It's y equals. So we definitely have to start with that. And then to find the horizontal asymptote, look at the EBM. and let x get bigger and bigger and bigger, and I want to know what happens to what's in that box. As x continues to get bigger and bigger and bigger, what happens to the bottom of the fraction if x is getting bigger?
The fraction is getting bigger.
Just the bottom part. What's happening to just the bottom?
Smaller.
So just look at that, and as that thing that you can see on the board gets bigger, that's in the bottom. So the bottom is getting bigger. The bottom is getting bigger, and when the bottom of a fraction gets bigger and bigger, what happens to the whole fraction?
Top gets smaller.
The whole thing gets smaller. Smaller and getting closer to what? Zero. Will it ever reach zero? No. Even if you take 120 and divide it by 600 billion, it doesn't, it's not zero, but it's getting closer to it. So that's your horizontal. Vertical asymptote. Okay, that's also an equation. And how does the vertical asymptote start? Is it y equals or x equals? Yeah, that's going to be x equals. And it's x equals whatever number would cause you to divide by 0. For that, you can look at the version where we combine them both together, or you can look at the original fraction separately. Does anyone see a number that would cause your denominator to be a 0? 0, yep. That's 1. And is there another number you could plug in?
Negative 20.
Negative 20, yep. Okay, so we've got the two asymptotes. We've got the EBM. And what else do they want? Oh, the zeros, or the roots. So we'll use a lot of different names for those. Zeros, roots. When you draw it on a graph, what is it visually? It's where the graph crosses the x-axis, or it's also called the x-intercept. So to find an x-intercept, which is what we're doing, we're finding the zeros, you plug in 0 for y. That's how you find an x-intercept. Plug in 0 for y. That's your y right there. Right? Sometimes we say f of x, g of x, or we're using t of x. That's my y. So I'm going to set this fraction equal to 0. I'm going to solve it. And those are my x-intercepts, which are my zeros. You working? There you go. Sorry. All right, so let's set that fraction equal to 0. 120x plus 600 over x times x plus 20. So set your equation equal to 0, and that's how you find the roots, or the zeros. There's only one way a fraction can ever come out to 0. What has to happen for a fraction to equal 0? The what?
Top is 0.
The top has to be 0, right? Anytime the top of a fraction is 0, you will get 0, right? 0 divided by 10 is 0. So we just have to figure out what makes the top 0, and that'll make the entire thing 0. That's what we want. Okay. 2 steps to solve for x there. What would be my first step?
Subtract 600.
Subtract 600. And then divide by just the 120. Okay, so with the x is okay where it is because we want to leave that. You cross those zeros off. And what's negative 60 divided by 12?
Negative 5. Sorry.
Negative 5. Yep. Okay. So x equals negative 5. And that's everything they wanted, except the graph. I'll do that next. So So we get the asymptotes, the EBM, the zeros, and now let's make a sketch. The reason we do all that first is because this kind of gives us an idea of what we're going to need for our window. I need to go over to negative 20. If I don't go that far, I'm not going to be seeing everything in this graph. Now remember, x was the speed of the car. So does negative 20 make sense for a speed? Could you have that, negative 20? No, you can't really have that. But this problem isn't really about the word problem right now. It's just about that equation, forgetting about it has anything to do with a real life problem. Right? It's just a math equation. So we are going to look at negative 20. I'll probably even go all the way to like negative 30. All right, so let's type it in. You can type in the original version, or you can type in the one where we combined everything together. I'm going to do the combined one because I think it's less parentheses for me to deal with. So I've got 120x plus 600. And so I don't have to even put an extra double set of parentheses in the bottom. I'm going to multiply that x out. X squared plus 20x. I think that's the simplest way for me to type it. Let's go to our window. We've got a vertical asymptote at negative 20. Let's go a little bit past it. X max, well, there really is no X max. We can go as high as we want for X max. Let's hit graph and see what it looks like. All right, so that is not a good window. And the reason I can tell is because when you graph, and you have two vertical asymptotes, you can't cross a vertical asymptote. So two vertical asymptotes should be separating my graph into how many pieces? If you had one vertical asymptote, it would separate it into two. Three, right? It's like every time you have a vertical asymptote, thinking of it as like cutting a piece of string. If you have a piece of string and you cut it once, you get 2. If you cut it twice, you get 3. So we should have 3 pieces to this graph. I can just barely kind of see the third piece right there. I think there's like 1 pixel that's lit up. So I got really lucky that I could see that, but I need to look a lot further down and to the left. So let's put this at like negative 50. And let's set the y min at negative 40. And let's see if we can see that third piece. There it is. So that was the left piece, the middle piece, and the right piece. Okay, that's a good window. All right, so we can see all 3 pieces. Not the only window. I mean, there's other windows you could use, but that one works pretty well. Any questions on how I use those numbers to get that window? All right. So if we were focusing on the word problem, let's just label these section 1, 2, and 3. Which section would we look at that would make sense in terms of our word problem? Why? Because it's positive, right? You can't have negative speed. So 1 and 2 are there because of the equation, right? We're looking at it mathematically. But if we want to look at it in terms of the real world problem, you should only focus on section 3. So that's what I'm going to do now. Okay, I'm going to get this ready because in the last part, we're going to go back to the word problem and we're going to figure something out. So let's zoom in now just on section 3. Okay, also, x max, let's set that at like, remember x is the speed, so let's just go up to 60 and see if that's enough. We don't need any negatives. And there's section 3. So what do you notice about, remember x is the speed of the car. what happens the faster that she drives in the car? What is this graph telling us happens?
Less time she has to travel?
Right, y is the time. So the faster we go on the x-axis, the lower the graph goes, and that's the time. So the less time it takes. If she starts driving really, really slow, the amount of time it takes goes way up. Right? Now, would the amount of time it takes for her to do this trip ever be 0? No. Mathematically, it can't be 0 because you have a horizontal asymptote right there. So that blue curve can never come down to the purple dotted line. And then practically it can never be 0 because, well, think about it, you're traveling between point A and point B. It can never take you 0 amount of minutes to go from one point to the other point. Okay, you can't do that. All right, so now they're giving us some information that we can use here. It says Sue has 2 hours to complete the trip. Find the speed she has to travel. We're going to do it graphically because we're going to do a lot more algebraically after this one. So let's do this graphically. Okay, so Sue has 2 hours to complete the trip. Find the speed she has to travel by car graphically. Well, here's the graph of the time it takes for her to do the trip, and we've got to see where that graph hits 2 hours. How would we do that? Yes, yeah.
So if time is the y-axis, right?
Yep, time is on the y-axis.
You would make a second line where it would be y equals 2, and
Yep.
you would just find where they intersect.
Exactly. So time is the y-axis, so we're going to put a mark at the 2 hour section. And now we just have to see where her time hits 2 hours by seeing where they cross. So second calc, intersect. Because they only cross in one spot, you just hit enter 3 times. And we just solved for x. That 46.46. What does that represent in our problem again? It's the speed of the car. Yes. So the question is asking what is the speed of the car. If it had asked for the train, we would have to add something to that number. We would have to add 20. Okay, but it didn't ask for the train, so we're just going to write it down. Find the speed she must travel by car. So Sue must travel at 46.46 miles per hour. And she will make the trip in exactly 2 hours. Okay, so we'll keep that graph in the calculator because we're going to use it to do one of the very last questions today. But we're going to kind of get away from this word problem for a little bit. Any questions on how we got the 46.46? All right. So that was solving graphically. Now I'm going to explain how you do it algebraically, and then we'll do an example. And I want to show you what can happen when you do it algebraically, something we got to be careful about. So now this is different. This is how to do it without a graphing calculator. Solving algebraically, you need to multiply both sides of the equation by a variable. Not always, but I would say like 95% of the time you're going to have to. So you may need, and by may I mean most of the time, you may need to multiply both sides of the equation by a variable. Now I think the rest of it's fine. when you multiply both sides by a variable, what that can do is it can create an extra answer in the problem that shouldn't be there. The original answer will still be there as well, but you might get an extra one. There's no way to avoid, when we do it with this method, there is no way to avoid that extra answer that shouldn't be there. That extra answer is called extraneous. It's an answer that you created because you multiplied both sides by a variable, but we need to cross it out and say that it doesn't work. So the only way that you would know that an answer to a problem is extraneous is if you check it. What's going to happen if it's extraneous when you check it? You're going to plug it back in, and it's probably going to cause you to divide by 0, which we can't do. That's generally how you know you created an extra answer that should not be there. So we just have to check our answers. So what we're going to try to do to make these problems a little bit easier is, instead of having fractions, first thing we're going to try to do is get rid of the fraction. If we can get rid of the fraction, this problem becomes a lot easier. So let me show you an example with just numbers in the denominator and how we can get rid of the fraction with numbers. And then we're going to do the same thing, getting rid of fractions that have letters in the bottom. Okay, so say we had 2x plus 2 over 3 plus x over 5 equals 3x over 15. Okay, I'm not going to solve this problem all the way through. I'm just going to show you how to convert this into something with no fractions in it. The goal is to multiply this, and that, all by the same thing. We want to multiply them by the LCD, least common denominator. So we have a 3, we have a 5, and we have a 15. What's the least common denominator? What's the smallest number you can think of that 3, 5, and 15 all go into? 15, yeah. And I just, instead of thinking of it as 15, I'm going to think of it as 3 times 5, which is 15. So what we're going to do is multiply everything by 15. But I'm going to write it as 3 times 5. So the first fraction gets multiplied by 3 times 5. Second fraction gets multiplied by 3 times 5. And so does the third one. They all get multiplied by 3 times 5. Right. Now, just look at the first one. You have 2x plus 2 divided by 3 times 3 times 5. Something's going to cancel out there. What's going to cancel out in this first fraction? 3, right? Because you have a divided by 3 and you have a times 3. You know what? I don't want it to look like you're raising to a power, so let me just put times 3 times 5. Just put it a little bit lower. Okay, so the 3's cancel out. How about in the second fraction? X divided by 5 times 3 times 5. The 5 cancels out. Yep. And the third fraction, 3x divided by 15 times 15. What cancels out there? The 15. So what you'd be left with now, you still have the 5 in the first one. That didn't cancel. That's 10x plus 10. In the second one, you're still left with the 3. That's a 3 times x. And in the third one, you're just left with another, just coincidence, 3 times x. Now I'm not going to finish from here, but you've got an equation that's a lot easier to solve because now it doesn't have any fractions. You just have to combine your like terms and then put all the x's on the same side and go from there. So that's exactly what we're going to do next with letters. Always going to have one thing that cancels out in each fraction, and that's going to make it a lot easier to solve. Okay, let's try this one. So one thing that you'll notice in that last problem, this denominator was the product of the other two. If that hadn't happened, like let's say this other number over here was a 13 instead of a 15. Well, then we'd have to multiply everything by 3, 5, 13. We would have had to multiply by all three. But we didn't have to because this denominator was the product of these two. So that's the first thing we want to check. Okay. We want to see if this denominator is the product of the other two. All right, let's look at that right-hand side, and let's see if it's like the 15, where it's the product of the other two. So we're going to factor it. How does x squared minus 4x plus 3 factor?
X minus 1 and X minus 3.
So yeah, it does. It factors as x minus 1, x minus 3. Because if you multiply that, you get x squared minus 3 minus 1 is minus 4. And negative 1 times negative 3 is positive 3. So that denominator is the product of the two that came before it. So it's just like the 3, the 5, and the 15. It's exactly the same thing. So I'm going to multiply this, and that, all by the same thing. What are all three of those going to get multiplied by?
X minus 1 times X minus 4.
X minus 1 times x minus 3. Yep. Don't do that out yet, because something is going to cancel everywhere. Just like the 3 and the 5, something canceled everywhere. Okay, so they all get multiplied by x minus 1, x minus 3. What is going to cancel in the first parenthesis?
X minus 1.
Yep, x minus 1 is gone. What's going to cancel in the second parenthesis, second calculation?
X minus 3.
The x minus 3. And on the right-hand side, what's going to cancel?
The X minus 1 and the X minus 3.
Right, the whole thing, all the entire denominator cancels out. Okay, whatever you're left with is usually a distributive property. So we got to distribute that out. What do you get if you distribute 2x to x? 2x squared. And what about 2x times negative 3?
Negative 6x.
Yep. Now, the next one is also distributive, but it's not going to change anything. Because all you're going to be distributing is plus 1. Important thing to notice, though, this symbol goes with that number. So if this was a minus, then I'd be distributing a minus 1. Okay? But it's not. It's a plus 1, so it doesn't change anything when you distribute. It's just x minus 1. And what's left on the right-hand side? 2. So now we're left with an equation that doesn't have any fractions in it, and the highest exponent in that equation is a 2. What do we call an equation where the highest exponent is a 2? Yeah?
Quadratic.
Yeah, it's a quadratic. So to solve a quadratic, we get it equal to 0, and then we have 3 choices. You can try to factor it, you can use the quadratic formula, or you can complete the square. You can do it any of those 3 ways. Okay, so first thing I'll do is combine my like terms. What's 6x? Negative 6x plus 1x.
Negative 5x.
Yep, negative 5x. And now when we're solving the quadratic, again, we got to get it equal to 0. So how would we move the 2 over to the left side? Yep, minus the 2. And negative 1 minus 2 is going to give you negative 3. Okay. And let's see if we can factor it. What would have to be my first term in each parenthesis that I could multiply together to get 2x to the second?
2x.
A 2x and a
X.
x, perfect. Now we have a negative in the middle, and we have a negative in front of the constant. What does that mean your signs are when you have negative, negative?
Double negatives.
Well, if we have a negative here and a negative here, when you multiply a negative times a negative, what would that give you?
Positive.
That'd give you a positive at the end.
Negative and positive.
Right, we need one of each. It could be positive, negative, or negative, positive. If it's wrong, we'll just have to switch it. And now 2 numbers that multiply to give us 3. 3 and 1. Okay, so I'm going to try them like that. And let's see. So we got 2x squared minus 6 plus 1. Perfect. Negative 6 plus 1 is negative 5. And 1 times negative 3 is negative 3. So you don't need quadratic formula. This one was factorable. All right. Now, once you factored it, what do you do with each one of these factors? When you're solving a quadratic? What's the only way you can multiply 2 things together and get 0 as the answer? What has to happen?
Which one is equal to 0?
One of them has to be 0. Either the first one, okay, so set that factor equal to 0, or the second one. What would we get for x when we solve that first equation? Yep.
Negative a half.
Yep, negative a half. And how about when you solve the second equation?
Probably 3.
3. Okay, that's a pretty typical problem. Okay, that's generally about the amount of work they take. Now we have to check those to make sure we don't have anything that would cause us to divide by 0. So let's look back at the original problem. I'll move away the purple line so it's easier to see what they were. Is there any issue with plugging either answer that we got back into the original question?
Yeah,
What happens if you plug in 3?
get 0.
Right, you get a 0 in that denominator and that one, in both of them. So 3 is not a solution. That is extraneous. Doesn't mean I won't ask you for it. Okay, I might still say, write down the answers to this problem, label any answers that need to be extraneous. So this is how you do it. This answer is fine. You can plug it in for x and you can check it. The only way this would be wrong is if you made a mistake in your arithmetic. But the negative 1/2 is definitely not extraneous. But the 3 is. Okay, so when you get to the end of a problem like this and you get 2 answers, there's 3 different cases. This is one of them. One answer works, one answer doesn't. What do you think another situation that could happen is? Besides one works, one doesn't. They both work, so neither one is extraneous. Or the last case, they both don't work. That would be a no solution problem. Yep. Those are generally the 3 things that would happen with this style of problem. Okay. Any question on that before we look at another one like that? Okay. All right, so let's look at this one. Again, very first thing you want to do is look at the more complicated denominator and see how it factors. Okay, so this time the more complicated denominator is the one all the way on the right. How does this denominator factor?
X plus 2.
Yeah, it factors into, if you factor out the GCF, it factors as x plus 2. So it is the product of the other two denominators, and that's generally the kind of problems you're usually going to see. If it wasn't, then it gets a little bit harder. Okay, so multiply all three of these. What are we going to multiply all three of them by?
X squared plus 2x.
Let's leave it not done out because something's going to cancel. So what would it be if you don't do it out?
X plus 2.
X plus 2. Yep. Always multiply it and leave it factored. Okay, so multiply everything by x plus 2. Just put all my parentheses in. And what's going to cancel in the first part? Yep, x is going to cancel. What's going to cancel in the second part? X plus 2. And how about in the third part? Both. Now do out whatever you have left, and just remember it's usually a distributive property. So first thing we've got to do is x minus 3 times x plus 2. So let's do that. X times x is going to give me x squared plus 2x minus 3x. It's 2x minus 3x. Negative x. And negative 3 times positive 2. Negative 6. Good. Okay, next one, not as complicated as a distributive. It's just positive 3 times x. What's positive 3 times x?
3x.
Just 3x. And on the right side, there is no distributive because it all canceled out. We're just left with what? Negative 6. Okay. Let's combine like terms. What's negative 1x plus 3x? 2x. Now I need to get it equal to 0 because it's a quadratic. So how would I move this negative 6 over here? I'm going to add it. And negative 6 plus 6 gives me how much? 0. So actually both of those are going to cancel. Now we're left with a quadratic, and we have the same three ways I mentioned before. Factor, quadratic formula, or complete the square. Is that factorable? Yeah, how would that factor? Factor, just factoring out a GCF. That's the easier kind of factoring. They both have an x in common. And now look at each factor. What number would you fill in here for x to make that come out to 0? 0. What number would you fill in there to make that come out to 0? Negative 2. So those are your two answers. Go back up. Is there any issue with plugging either one of those answers back into the original problem? Yeah, which one? 0. We can't plug in 0.
Both.
Both. Or negative 2. Because they cause you to divide by 0. So that means both of these answers are what? They're both extraneous. So what that means is you didn't find any answer to this problem. There was no solution. sometime in math you see this symbol. This symbol means no solution. It actually means technically empty set. So the set of answers that would make this problem true is empty. There are none. No solution. Okay, so that's the case where they both don't work. So we did both don't work, and then we did one works and one doesn't. The only one we didn't do is where they both work. Okay, question on that one before we look at the last thing we did. Okay, so the last thing we're going to look at, we're going to go back to the word problem again. All the information is the same. So she's still driving 30 miles by car, 90 by train. Train is 20 faster than the car. So none of that's changing. But something's really different with how they've asked this question. How did they ask this question in a different way than the first one?
They're asking for more than one rate.
So they're asking, at what possible rates could Sue travel? So yeah, why is it going to be more than one rate?
Because it's a train and the car. So they're asking for the rate of the train and the rate of the car. And there's a less than.
Right, it's because there's a less than. Right? So that means it's not an equal to. We're now doing a problem that's an inequality. Okay, we're not going to get an answer like x equals 55 miles an hour. We're going to get an answer like x is less than 55 miles an hour, or x is greater than 55 miles an hour. It's not an exact answer. Okay? So they want to know what speed she would have to travel at to complete the trip in under 2.5 hours. So what would I have to change here to represent what's happening in the word problem now? I've got to change one of those two graphs.
Y equals 2 becomes y equals 2.5.
Right, we don't want to know 2 hours anymore. We want to know 2.5 hours. So the problem starts off the same way. Graph each of them. And you even still have to find where they intersect. Okay, so that part's the same. So intersect. And they intersect at 34.88 miles per hour. So how would I write the answer? At what possible speed does Sue have to travel at to complete the trip in less than 2.5 hours? Yes. So Sue's speed must be greater than 34.88. That's the answer to the question. Now, some people think, well, yeah, but it said less than. That's for the time to be less than 2.5 hours. That doesn't mean her speed has to be less than. If she goes slower than 34.88, she's going to be on this part of the graph. That part of the graph is where it takes longer than 2.5 hours. That's not what we want. We want Sue to be somewhere on this part. Now, we also said greater than 34.88. That's exactly what it should be. If this question said, what speed does Sue have to travel at to complete the trip in 2.5 hours or less? What would change about how I wrote that? It would have been greater than or equal to 34.88. Yeah. But it didn't say 2.5 hours or less. It said less than 2.5 hours. Okay, so you just have to read it carefully to know what inequality symbol you need to use. Okay, so rational inequalities. So we're moving on from equations. We're finishing with inequalities. We are going to solve these graphically. Okay, so we're not going to do the multiply by the LCD kind of thing. We can't do that. Okay, so we're going to solve it graphically. Remember, when you solve graphically, there can either be hidden behavior that you have to zoom out to see. So remember when I had that 1 pixel on the screen? I didn't have enough of the screen to see what was going on. I had to zoom out more because what was off the screen was hidden. Or sometimes I might have to zoom in so that I can get a closer look at what's happening. So the point is always make sure you zoom in or out, whatever you think you need to do in that problem, to see the whole thing. And you will see some directions in the homework that say use a sign chart when you get to these rational inequalities. We're not doing the sign chart. Okay, so when it says use a sign chart, just use your graphing calculator. Does everybody have that part? Okay. Let's see what we got left. Let's do this one. Okay, when you type it, be careful. There's a lot to type in there. Everything on the left is going to go in Y1. Everything on the right is going to go in Y2. Because the numerator and denominator have multiple terms in them, you're going to have to put parentheses, just like I did in this one. So, 2x squared plus 6x minus 8. And we're going to divide by 2x squared plus 5x minus 3. Okay, so you get your left side in Y1. Put your right side in Y2. And we're going to be looking for where the blue graph is under the red graph, if you use the same color as I did. We start with zoom 6. Okay, so there's our graph. Let's take a look at that. So this graph is in 3 pieces. Let's look at piece 1, 2, and 3. So we want to know where we are under the red line. Let's look at piece 2. What do we think about the second piece of the graph? It's always above the red line. So we don't ever even really have to look at that section. If it said, where are we above the red line, then yeah, we would. Okay, but piece 2 is never less than 1. It's always above. It actually looks like it's always above 2. Okay, so we don't have to look at that piece. How about pieces 1 and 3? Do they ever look like they're under the red line?
Yeah.
Yes. So now the question is, are they always under the red line? Or at some point, if we keep going, will they go above the red line? So now we just have to check that on the calculator. Let's start with piece 1. I want to look at what happens if I keep going to the left. I want to know if I stay under the red line. What would be an x value further to the left that I could use to check that? Even if it's off my screen. Negative 100. I'm at 0.9946. Am I under the red line still? Yeah, basically, is this number below that number? Okay, so we're still under it. Let's go more. Let's go negative 1,000. 0.995. Am I still under it? Okay, if I've gone this far, I'm probably never going to go above it. Okay, I go all the way to negative 8,000. I'm at 0.9999. I still haven't hit it. I probably never will. So section 1 is going to stay underneath the red line all of the time. The only thing we have to look at carefully is we have a vertical asymptote, I would say right about there. And it looks like we've got another one on the other side. I would say, I'm just trying to put it in between the two. Right about there. So we went all the way to negative 8,000. We still didn't go above the red line. How far to the left do you think I could keep going? Forever. So if I keep going to the left forever, I would reach what? Infinity's to the right. Negative infinity. So that's part of our answer for section 1. Negative infinity up to, now we can't keep going to the right forever because section 1 doesn't go to the right forever. If you go too far to the right, you're going to end up on section 2. Section 1 stops at a number. What number does it look like section 1 stops at if you keep heading to the right?
-3.
Yeah, and we can check that by typing it in, and we get an error. That's because there is a vertical asymptote at -3. Yep. So section 1 goes to the left forever, and it goes right up to, but you can't include -3. So that's from section 1. Or we all agreed there was another piece that looked like it's under the red line, and that was section 3. Now, let's start with the lowest x value you could pick and still be on section 3. If you pick -1, you're not going to be on section 3 anymore. You'd be on section 2. How far to the left does section 2 go before it looks like it just stops? It looks like it's about 0.5. Okay? It's always going to be an easy number to figure out. In this case, it's not going to be something like 0.37. It's not going to be a weird number. It's going to be something that if you graph it, you'll be able to tell easily. And it is. It's 0.5. 0.5 is another vertical asymptote. So the lowest we can go is 0.5. Now, let's start going to the right and see if the blue line goes above the red line. We don't want it to. What would be a number I could check that goes to the right? 100? Are we under the red line? No. So we went above the red line somewhere. So what we want to do now is see where. Maybe it intersects like somewhere in here. Let's try to find the intersection point. Let's do intersect. Move our cursor somewhere over here. And they do. They do intersect. It intersects when x is 5. So 5 is the highest that you can go. And let me kind of exaggerate it. It's 1, 2, 3, 4, 5. So basically it does something like this. It's a little exaggerated, but right at the number 5, it goes above. Not that quickly, but I'm just trying to show it. Okay. So to stay on section 3, we can go as low as a half, and we can go right up to number 5. But we can't include 5. The reason I can't include it, that's not an equal to. If it was an equal to, then I would have put a bracket on the 5. That's the only thing that would have changed in this problem if that had an equal to. You never include a number that gives you an error, ever. You always put a parenthesis on a number that gives you an error, and you never put a bracket on an infinity because you can't reach it. So these 3 parentheses have to stay no matter what. But this one could have been a bracket if the problem was written a little different. And that was from interval 3. And that's your answer. So that describes all the sections of the graph that are under the red line. Question on that? So that's how you'll solve rational inequalities. Do not do the sign pattern method. I didn't teach you that. So it says it in the book. Just do exactly what we did on your calculator. All right. So that's the homework for tonight. So it's 1 through 13 odd. And then 20, 22, 24, 28, and 31. We'll go over that tomorrow. That was probably the longest section for this week because 4.4, we're going to take it, and it's the same length as this, but we're going to do it in 2 days. So we're going to be able to go a little bit slower through the next section.